Hi everyone, my name is Kurdo from University of Toronto. Today I would like to present the work Catch the Ball Accurate High-Speed Motions for Mobile Manipulators by Inverse Dynamics Learning. This work was done by me and my colleague Karime under the supervision of Professor Florian Shkurti and Professor Schoellig. As capabilities of robots improve, applications involving the use of robot arms in dynamic and unstructured environments have become increasingly valuable. Household cleaning, warehouse management, and automation of factories greatly increase the efficiency and reduce the risks for human operators. Fast planning and accurate control are a crucial enabling technology for all these applications. So the goal of this project is to develop methods of real-time trajectory generation in dynamic environments and accurate joint control for high-speed trajectory tracking for mobile manipulators. We focus on the ball catching problem, which is a typical benchmark task for accurate high-speed motions. Within a fraction of a second, the robot needs to predict the ball's trajectory, generate catching motions, and accurately track it with the mobile manipulator. This task is very challenging due to the following three characteristics. First, we have real-time computation constraints. On average, the ball will only be in the air for about 1 second. This puts a hard constraint on the computation time of all components. Second, we have a tight control requirement here. The successful catching requires a precision of 16 millimeters in position and 3 milliseconds in time in this project. However, we do not have high-performance hardware in this project. The wheel-driven base that we are using has much lower control accuracy than ARM. Thus, extra efforts are needed to improve the base control performance. A large body of work has been devoted to ball catching with a fixed base manipulator. Early pioneering work in this field used heuristic methods for selecting the catching point, like the nearest point in the ball trajectory, or the intersection point of the ball trajectory with a given virtual plane. These methods are easy and fast, but it may not lead to the optimal catching motion. Recent work and our work used more computationally expensive methods for optimal catching point selection, like sequential quadratic programming. For trajectory generation, literature used different parameterization schemes, like third-order polynomials and trapezoidal velocity profile. These methods put extra but unnecessary constraints on the robot motion. In our paper, we treated this as an optimization problem and used quadratic programming to generate the trajectory. This gives us more flexibility in the robot motion. As for the low-level joint control, people usually use feedback PID controllers and low-level torque controllers. In this paper, we add an inverse dynamics learning modular to the closed-loop system to further increase the control performance. The work most similar to ours is the mobile humanoid, rolling Justin. To the best of our knowledge, this is also the only robot doing mobile manipulator ball catching, except us. Rolling Justin can catch a ball while the base is moving in one direction, but our algorithm can enable the base to move in the whole plane. Meanwhile, the Rolling Justin project has customized high-performance hardware, while we just use off-the-shelf mobile manipulators, so it may be easier for our approach to generalize to other robotic platforms. In this work, we focus on real-time motion planning and accurate joint control for mobile manipulator ball catching. Our contributions are twofold. First, we propose an algorithm framework for ball catching. It has a bi-level real-time motion planning scheme and a learning-based low-level joint controller. Second, we have extensive evaluation of the performance of the proposed framework on the mobile manipulator, which can be a resource for similar system designs. Experimental results show that we have a success rate of 85.33%, better than the state-of-the-art 80%. Now let's have a look at the problem statement in math. We use Q to denote the robot configuration vector, QA to denote the 6 joint angles of the arm, and QB represents the Cartesian coordinates of the base. We do not use the yaw rotation of the base because it is too slow for the ball catching task. B and B dot represents the ball's position and velocity in the world frame. WPE and WDEE are forward dynamics functions of the mobile manipulator. They calculate the end effector's position and the axis orientation in the world frame. So our problem is that given initial robot configuration, ball state, and time, We want to catch the ball at a certain catch time, such that the position of the end effector equals to the position of the ball, and the axis of the end effector aligns with the ball's velocity vector. Now let's look at the system diagram. The ball estimation modular receives Wycombe measurement and outputs current ball states and future ball trajectory prediction. The planning modular receives current system states and ball trajectory prediction and outputs smooth drawn trajectories. The control modular receives drawn trajectories and generates control commands to the onboard orbital controllers. So now let's first look at the ball estimation modular. The flying ball's motion is modeled as a point mass under the influence of air drag and gravity. The air drag is modeled as proportional to the square of the speed, and the drag coefficient is estimated via a recursive least square estimator. For the ball state estimation, we use a discrete time Kalman filter. It only considers the air drag in the state prediction step via a one-step integration, and this estimator neglects the air drag in other filtering steps. This is a compromise between computation efforts and estimation accuracy. For ball trajectory prediction, we do a numerical integration of the ball dynamics to a given horizon. Now let's look at the planning modular. The planning modular consists of two planners. The high-level planner is in continuous time. It receives ball trajectory prediction, current rubber states, and current time, and calculates the optimal catching configuration and time. The low-level planner is in discrete time. It receives the optimal catching configuration and time from the high-level planner and the current rubber states and time. It outputs the position trajectory for each droid. To tackle these two planning problems online, we need to first make three simplifications here. First, we assume that we have quadratic functions. They are easy to deal with and can cover most of our user specifications. Second, we assume that there are no nearby obstacles and no arm self-collision. Hence, no obstacle or self-collision check is needed. The only collision that may happen is the collision between the arm effector and the mobile base. To avoid such a collision, we require the arm effector to stay inside the semi-cylinder centered on the arm base. Here, APEX, APEY, and APEZ is the effector's position relative to the rotor frame. The last simplification is kinematic planning. We use kinematic models to depict the droid motion instead of dynamic models. This simplification works well in experiments, as long as we choose droid boundary values conservatively and low-level droid controls work properly. We use the double integrated model as the kinematic model of a single droid. With these three simplifications, the high-level planner can be expressed as a nonlinear, non-convex optimization problem. We want to minimize a user's defined cost function, and they have several constraints here. This is the collision avoidance constraint. This is for the task success. And this is to ensure that the final catch configuration is reachable from the current configuration within the specified time. In our paper, we assume that the maximum droid movement is proportional to the distance that the droid can traverse under the travel velocity profile. Other assumptions can also be used. We use the SQB method to solve this problem. The low-level planner can be expressed as a quadratic program. For the ITH droid, we first discretize the position and acceleration trajectory with a predefined step size gamma. In this optimization problem, our decision variable is the acceleration sequence, because the position can be obtained from the acceleration by integration. The first constraint we have here is the kinematic model. The second constraint is kinematic boundary value. The last constraint is the initial and desired final pose conditions. The last position needs to equal to the given optimal catching configuration, and the velocity needs to be 0. Now let's look at the joint control modular. The task of the low-level joint controllers is to accurately track joint trajectories generated by the planning modular. As mentioned before, accurate tracking is hard for the mobile base. So here we use the inverse dynamics learning technique to increase the robot's control performance. It uses deep neural networks as an add-on blocks to the baseline feedback control system to achieve a unity map between the desired and actual outputs. A general inverse dynamics model receives system's current states and desired states, and outputs required action. In our scenarios, for a GTH joint at the discrete time system at the discrete time step k, the neural network's inputs are the joint current position and the desired position at step k plus r. The neural network's output is the modified desired position at step k plus 1. R here is the system's relative degree. For discrete time systems, the relative degree can be intuitively understood as time delay, which can be determined easily from experiments. Next, let's look at our experiment setup and results. We validate our algorithms on a real mobile manipulator. It is a UR10 arm mounted on a reachable mobile base, and we place a cup on the gripper to catch the ball. The cup's diameter is close to the ball's diameter, which causes the tight control precision requirement. We use the Y-con system for ball state measurement and a laptop for computation. In the experiment, we have 3 different robot initial configurations, as shown here. For each initial robot configuration, we throw the ball from 5 different locations, 5 throws for each location. So in total, we have 75 tosses, and this is the 75 ball trajectories. The robot catches 64 of these 75 ball trajectories, which is a success rate of 85.33%. Just a quick note, there is a typo in the paper. The robot catches 64 instead of 65 of the tosses. But the success rate 85.33 in the paper is correct. Now let's look at the video. As presented in the video, there are several reasons of failures, like inaccurate ball trajectory prediction, tracking errors, and failure of the high-level planning algorithms. In other words, the malfunction of any component will result in a failure. As of future work, we want to use dynamics level planning instead of kinetics level planning. The usage of kinetic model makes the planning model easier, but the planner needs to be conservative to ensure that kinetic models work. So if we are using dynamic models, the planner should be able to generate more aggressive motions that the joint controllers can accurately track. We are also exploring deep reinforcement learning algorithms for the ball catching task. This may lead to arbitrary object catching in the future. Thank you for listening. For more interesting research works and core robotic projects, please visit our website and follow us on the social media sites.